Hi, I'm Arash, a software engineer in the Bay Area. A topic that I've noticed some folks may find intimidating is how do variables or arrays sit in memory and how operations on them can affect time complexity. Let's go over those with some simple Python examples. Imagine your computer memory is like a bunch of shelves that sit on top of each other. You can put things in those shelves, you can take things out of them, and the way you would refer to them is like first shelf, second shelf, and so on. Let's go through an example. If I define a variable like x equals 257, that 257 goes and sits in some empty memory location, and Python pulls out a scratch sheet of paper and writes down that memory address that it just used to store that value. This way, the next time that Python needs to grab x, it knows where to look for it. Throughout this video, I'm going to use Python's ID method, and let's assume that the value that's returned is the same as the addresses that we have. So this large number that's returned is the same as saying address 1 in our picture. Let's trace a couple of other examples. For this video, assume that we can only fit small integers or single characters in each shelf. Also keep in mind, memory slots are not necessarily filled sequentially in reality. We are abstracting away some complexities and concepts like garbage collection, interning, and so on. If you're interested, I can make separate videos for those. Okay, let's go through an array. It's pretty much the same except that we go through that flow several times. So we put the array elements in empty memory locations and record the memory addresses. One question that may come to mind is, if we have the starting point and the length, why can't we just calculate the rest of the memory addresses? Let me show you with an example. So if I define another variable and that variable sits right after the last element of the array, now my array runs out of room to grow. So if I try to append a new value, then I have to put it a little farther from the last element. So the only way for me to maintain the order of the array is to have another pointer pointing to that next location. If you're interested in knowing more about these topics, you can read about static versus dynamic arrays in languages like C. Now if I pop an element from the end of the array, I'm sure you can guess the length goes down by 1 and the pointer to the last element goes away. I'm going to append that value back. Let's talk about time complexity for a second. So every operation that we just did, appending to the end, popping from the end of the array, takes constant time. We show that by denoting O of 1. O of 1 doesn't necessarily mean a single operation, it means a constant number of operations, constant relative to other things. So if our array had 1,000 members, still adding one member to the end of it would take the same amount of time. In contrast to that, we have something like linear time complexity. So let's go through it with an example. So if I try to insert a value in index 1 of this array, for example 33 in this case, Python will have to shift down every memory address that it has stored to open up some space for, in this case, address 10 to fit in there, and it can maintain the order of the array. As you can imagine, this is more expensive, and if I had an array that had 1,000 members, it would be a lot more expensive. So in this case, we say this operation is of O of n. So that means the time complexity grows linearly relative to the size of array in this case. Now if I try to pop an element from index 1 in this array, I'm sure you can guess every element would have to shift up by 1 to maintain the correct order of the array, which would also have linear time complexity. If you found the video helpful, please like and subscribe, and leave a comment if you're interested in a video on a different topic. See you soon.